Hello dear students, all of you welcome to Vidyan classes. Today we will discuss some important very short answer type questions. Question number 1. If capital A is 3 cross 4 matrix and capital B is a matrix so that A dash B and B A dash are defined, then B is of the type dash. A is a matrix of order 3 cross 4. What is the order of the matrix capital B? So that A dash B and B A dash are defined. It is given by A is a matrix of order 3 cross 4. What is the order of the matrix capital B? So that A dash B and B A dash are defined. Solution. Let order of matrix B is M cross N. Given order of capital A is 3 cross 4 implies order of A transpose, that is A dash, is order of A is 3 cross 4, order of A transpose is 4 cross 3. Since if rows changes to columns and columns changes to rows, the matrix obtained is called transpose matrix. A dash B is defined. A dash B is defined. Transpose of A into B is defined. Matrix multiplication is defined. If the column of first is equal to row of second, column of first is equal to 4 to 3, 3 to 3 means M to N. Since A dash B is defined, implies matrix multiplication is defined. Column of first is equal to row of second. The column of first, that is 3, is row of second, second B implies M is equal to 3. Again, B A dash is defined. Column of B is equal to row of A dash. Column of B, that is N, implies N is equal to row of A transpose, that is 4. B A dash is defined. Column of B, that is N, is equal to row of A dash, that is 4. Order of B is dash. Then B is of the type dash. So, order of B is M cross N, that is 3 cross 4. Then B is of the type dash, that is 3 cross 4 is the answer. So order of B is 3 cross 4. Clear? Okay. Next question number 2. If capital A is a matrix having elements 1 0 0 0 1 0 A B minus 1, then A square is a dash matrix. Solution. Capital A is given by capital A is a matrix having elements 1 0 0 0 1 0 A B minus 1. A square is equal to A into A, which is same as 1 0 0 0 1 0 A B minus 1 into matrix having element 1 0 0 0 1 0 A B minus 1. A square is equal to A into A. By the matrix multiplication rule, go through row 1. Go through row 1, come down in column 1, multiply the corresponding elements and add them. It gives 1 into 1, that is equal to 1, 0 into 0, that is 0, 0 into A, that is equal to 0. Next, go through row 1, come down in column 2, multiply the corresponding elements and add them. 1 into 0, that is equal to 0, 0 into 1, that is 0, 0 into B, that is equal to 0. Next, go through row 1, come down in column 3. Multiply the corresponding elements and add them. 1 into 0, that is 0, 0 into 0, that is 0, 0 into minus 1, that is equal to 0. So it is 0 plus 0 plus 0. Clear? Next, go through row 2, come down in column 1, multiply the corresponding elements and add them. 0 into 1, 0, 1 into 0, 0, 0 into A, that is equal to 0, so it is 0 plus 0 plus 0. Next, go through row 2, come down in column 2, multiply the corresponding elements and add them. 0 into 0, that is 0, 1 into 1, that is equal to 1, 0 into B, that is equal to 0, so it is 0 plus 1 plus 0. Next, go through row 2, come down in column 3, multiply the corresponding elements and add them. 0 into 0, 0, 1 into 0, 0, 0 into minus 1, that is equal to 0. So it is 0 plus 0 plus 0. Similarly, go through row 3, come down in column 1, then column 2, then column 3. A into 1, that is equal to A. B into 0, that is equal to 0. A into 1, B into 0, minus 1 into A, that is minus A. Go through row 3, come down in column 2. A into 0, that is 0. B into 1, that is B. Minus 1 into B. A into 0, that is equal to 0. It is B. B into 1, that is B minus B. Next, go through row 2, row 3 and come down in column 3. A into 0, that is 0. B into 0 equal to 0. 0 minus 1 into minus 1, that is plus 1. So it is 0 plus 0 plus 1. It is 1 0 0 0 1 0 0, 0, 1. It is the unit matrix which is same as I3. We can write I or I3. I3 means it is a unit matrix of order 3. A square is a unit matrix of order 3. Is a unit matrix is a unit matrix. So the correct answer is a unit matrix. Is a unit matrix. Clear? Okay. Write down. Question number 3. For 2 cross 2 matrices A, B and I, if A plus B is equal to I, 2A minus 2B is equal to I, then find A. Given A, B and I all are 2 cross 2 matrices. That means order of A, B and I is 2. A plus B is equal to I, 2A minus 2B is equal to I, then find A. Let A plus B is equal to I. I is the unit matrix or identity matrix, which implies 2 A plus B is equal to 2I, which gives 2A plus 2B is equal to 2I, is equal to 2I. Since matrix multiplication is distributive, since alpha A plus B, alpha is a scalar, alpha A plus alpha B. It is equation 1. Also we have two A minus 2B is equal to I. It is equation 2. Equation 1 plus equation 2 implies 2A plus 2B plus 2A minus 2B is equal to 2A plus 2B is equal to 2I, 2A minus 2B is equal to I, which gives 3I. Using the properties of matrix addition, using the properties of matrix addition. Matrix addition is commutative, matrix addition is associative. A plus 0 matrix is equal to A. 0 matrix is called the additive identity. A plus minus A is equal to 0 matrix. Minus A is called the additive inverse of A. Using the properties of matrix addition, the LI side gives 4A is equal to 3I, which implies 1 by 4, 4a is equal to 1 by 4, 3i. Matrix multiplication is closed. Multiply 1 by 4, 1 by 4, both the sides, which equal to, which implies a is equal to 3 by 4 I. Clear? I the unit matrix of order 2. A is equal to, which implies A is equal to 3 by 4. I means unit matrix of order 2 is equal to 3 by 4, 0, 0, 3 by 4. Therefore, A is equal to 3 by 4, 0, 0, 3 by 4 is the answer. Clear? Okay. Next, question number 4. Find the value of x so that the matrix product this and this matrix equals an identity matrix. Two, 0, 7, 0, 1, 0, 1 minus 2, 1 into minus x, 4x, 7x, 0, 1, 0, x minus 4x, 2x. It is a matrix of order 3, it is also a matrix of order 3, equals an identity matrix. That means unit matrix. The result will be I of order 3. 1, 0, 0, 0, 1, 0, 0, 0, 1. The product of this and this is the identity matrix. Using matrix multiplication, go through row 1, come down in column 1, multiply the corresponding elements and add them. 2 into minus x minus 2x, 0 into 0 that is equal to 0, 7x plus 7x, minus 2x plus 7x, it gives minus 2x plus 0 plus 7x, which gives 5x. We have to find out the value of x. Find the value of x. It is a matrix of order 3. It is not necessary to find out all the elements of the product matrix. Here 1, 0, 0, 0, 1, 0, 0, 0, 1. It is not necessary to find out all the elements of the matrix product. Two matrices are equal if their corresponding elements are equal. A11 is 5x, A11 is 1. Two matrices are equal if their corresponding elements are equal. In left hand side, A11 is 5x, in right hand side, A11 is 1. So 5x is equal to 1. Implies x is equal to 1 by 5. Is the answer. Clear? matrix, two matrices are equal if their corresponding elements are equal. Multiplying this and this matrix by the matrix multiplication, go through row 1, come down in column 1, multiply the corresponding elements and add them. 2 into minus x, that is minus 2x, 0 into 0, that is equal to 0, 7 into x, that is 7x. Adding the products of the results, it gives 5x, which is the element of A11. The right hand side is the unit matrix. A11 represent 1. Two matrices are equal if their corresponding elements are equal. So 5x is equal to 1, x equal to 1 by 5. Clear? Next, question number 5. If A is a unit matrix of order 3, a square plus 2a is equal to dash. Given A is the unit matrix of order 3, 0, 1, 0, 0, 0, 1. It is a unit matrix of order 3 which is written as I3 or I. I3 represent the unit matrix or identity matrix of order 3. So I is equal to A square which is equal to A into A which is equal to I into I which is equal to I square is equal to I. I into I is equal to I. A square which is equal to I is equal to A is equal to A. So A square plus 2A which is same as A square is equal to I which is equal to A plus 2A which is equal to 3A is the answer. So the correct option is 3A. Clear? Okay. Note down. Next, question number 6. If AB is equal to A and B is equal to B, then show that A and B are idempotent matrices. What is idempotent matrix? Note, let capital A is a square matrix. Capital A is a square matrix. First, orthogonal matrix. What is orthogonal matrix? Capital A is said to be orthogonal if A into A transpose is equal to identity matrix. That means unity matrix. The order of I is same as order of A. A dash represent the transpose of A. A is a square matrix into A transpose is equal to I. A is said to be orthogonal if A into A transpose is the unit matrix where A and I have the same order. Second, nilpotent matrix. A is said to be nilpotent matrix if a to the power p is equal to 0 matrix. For the least positive integer p. Capital A is said to be nilpotent matrix if a to the p is equal to 0 matrix for the least positive integer p. Third, idempotent matrix. What is idempotent matrix? Capital A is said to be idempotent if idempotent matrix if a square is equal to a. A is said to be capital A is the matrix is said to be idempotent matrix if a square is equal to a. Clear? Last, involuntary matrix. The square matrix capital A is said to be involuntary. A is said to be involuntary matrix if a square is equal to I. A square is equal to I. First, orthogonal matrix A is said to the square matrix capital A is said to be orthogonal matrix if A into A transpose is equal to unit matrix. Nilpotent matrix, the square matrix capital A is said to be nilpotent matrix if A to the p is equal to 0 matrix for the least positive integer p. Idempotent matrix, the square matrix capital A is said to be idempotent matrix if A square is equal to A. Involuntary matrix, the square matrix capital A is said to be involuntary matrix if A square is equal to unit matrix. Here we have to prove A and B are idempotent matrices. It is given by AB is equal to A and BA is equal to BA. A and B are two square matrices. Prove let AB is equal to A, BA is equal to B. To show A and B are idempotent matrices, which implies by the square matrix capital A is said to be idempotent matrix if A square is equal to A. We have to prove A and B are idempotent matrices, which implies by A square is equal to A and B square is equal to B. Now ABA AB is equal to A into A. Since AB is equal to A, it gives A into A, which is equal to A square. A into A is A square, which implies BA is equal to B, which is same as A square. Since BA is equal to B, BA is equal to B. First we write AB is equal to A, it gives AA, which is same as A square. Again, ABA is written as A into B, since BA is equal to B, which implies AB is equal to A is equal to A square. Since AB is equal to A. Clear? A square is equal to A, so A is idempotent matrices. According to the definition, A is the square matrix capital A is said to be idempotent matrix if A square is equal to A. Again, BAB is the same as B into B. Since BA is equal to B, which is same as which is equal to B square. Since B into B is equal to B square, which implies B into AB. AB is equal to BAB, which is B is taken as B into B, that is equal to B square. In the left hand side, AB is equal to A. AB is equal to A. B A is equal to B square. Since AB is equal to A. Since AB is equal to A. First B is equal to B. It gives B into B, that is B square. Then AB is taken as A. It gives BA is equal to B square. But BA is equal to dash. BA is equal to B is equal to B square. Therefore, A square is equal to A, B square is equal to B. Therefore, A and B are two idempotent matrices. Here, since A square is equal to A, B square is equal to B, according to this condition, A and B are two idempotent matrices. Clear? Okay. Write down. Question number 7. Prove that A is the involuntary matrix if and only if I minus A into I plus A is equal to 0 matrix. We have to prove this product is equal to 0 matrix when A is involuntary. Again we will prove A is involuntary, that implies the product is equal to 0 matrix. Let A is involuntary matrix. Implies A is by the definition A square is equal to I. To show I minus A into I plus A is equal to 0 matrix. Taking A is the involuntary matrix, we have to show this result. Is equal to 0 matrix. I minus A into I plus A. It gives I square minus A square. Using the properties of matrix product. Using the matrix product is the associative, matrix product is the distributive, matrix product is the associative with respect to scalar. Using the properties of matrix product, it gives I square minus A square, which gives I square is same as I, so it gives I minus A square, which is equal to 0 matrix. Since A is involuntary matrix, since A square is equal to I or I minus A square is equal to 0 matrix. Clear? So A is involuntary implies the product of the two matrices is equal to 0 matrix. Conversely, let I minus A into I plus A is equal to 0 matrix. Using the property using the properties of matrix multiplication, using the properties of matrix multiplication, the left hand side gives implies I minus A square is equal to 0 matrix, which implies A square is equal to I. Using properties of matrix addition, I minus A square equal to 0 matrix. Using property of matrix addition, it gives A square is equal to I. Matrix addition is commutative, matrix addition is associative. 0 matrix is the additive identity of any matrix. Minus A is the additive inverse of any matrix capital A. Clear? A is involuntary implies this. Conversely, this equal to 0 matrix implies A is involuntary. If and only if means implied and implied by. This implies to this and this implies to this. Therefore, A is involuntary implies and implied by. That means if and only if I minus A into I plus A is equal to 0 matrix. Clear? Clear? Okay. Next question number 8. Solution. If A is involuntary, then half of I plus A and half of I minus A are idempotent, and half of I plus A into I minus half of I minus A is equal to 0 matrix. Given solution or proof. Question number 8. Proof. It is given by A is involuntary. Let capital A is involuntary. let capital A is involuntary, which implies A square is equal to I. A is the square matrix, capital A is said to be involuntary if A square is equal to identity matrix. A and I have the same order. To show this and this are idempotent. Idempotent means A square is equal to A. Let capital B is equal to half of I minus plus A and capital C is equal to half of I minus A. To show B and C are idempotent. To show B and C are idempotent, which implies by B square is equal to B and C square is equal to C. Now B square, which is same as half of I plus A whole square. That means B into B. B square means B into B. B square means B into B, which is equal to half of I plus A into half of I plus A, which is same as 1 by 4 into I square, that is equal to I plus 2AI plus A square. Clear? Using the properties of matrix product. Matrix product is associative, matrix product is distributive. Using the distributive properties, it gives this and this. Also, AI is equal to IA. Also, AI is equal to IA is equal to A, which is same as, and I square is equal to I. Using the properties of matrix multiplication, it gives this result, which is same as 1 by 4 A square is equal to B is given by this, which is same as A square is equal to I. 1 by 4 2I plus 2AI. AI is equal to A, 2A. which is same as 1 by 4 I plus A into 2. Matrix product is distributive with respect to scalar, which is equal to 1 by 2 I plus A, which is same as B, which is same as B, implies B square is equal to B. Therefore, B is involuntary matrix. Again, to show C square is equal to C. C square is equal to C. C square is equal to C into C, which is same as half of I minus A into half of I minus A. Matrix product is associative with respect to scalar alpha AB, which is same as alpha A into B, which is same as alpha, which is same as A alpha B. So you can write 1 by 4 I square is equal to I minus to AI is equal to A. Similarly, we can show I minus 2A plus A square, which is same as 1 by 4 2I minus 2A, which is same as 1 by 2 I minus A. Since matrix product is distributive with respect to scalar, these are the properties of matrix product alpha into A plus alpha into B. Using it is sufficient to write using the properties of a matrix product. Half I minus A is equal to this, which is equal to capital C. Therefore, so B square is C square is equal to C square is equal to C square is equal to C. Therefore, C is involuntary matrix. Next, we have to show C is involuntary. Since B square is equal to B, B is idempotent. Sorry, it is given A is involuntary. I square is equal to I. Since B square is equal to B, idempotent matrix. Here is idempotent. Since C square is equal to C, therefore C is idempotent. Next we have to prove the product is a zero matrix. Half of I plus A into half of I minus A, which is same as 1 by 4. Since matrix product is associative with respect to scalar, I plus A into I minus A, which is same as 1 by 4 I minus a square using the properties of matrix product. Using the properties of matrix product, it gives 1 by 4 I minus a square. I minus a square, which is same as 1 by 4 into 0 matrix, which is equal to 0. 0 matrix, since a square is equal to I. Since A is involuntary, a square is equal to I minus a square is equal to 0 matrix. So the 1 by 4 into 0 matrix is equal to 0 matrix, which implies as half of, therefore half of I plus A into half of I minus A is equal to 0 matrix. Therefore, the given statement is proved. If A is involuntary, then this and this are idempotent. That means it is taken as B, it is taken as C. Since B square is equal to B and C square is equal to C, implies this and this are idempotent, and using the properties of matrix multiplication, it gives 0 matrix. Hence, the statement is proved. Note down. Note down. Next, question number 9. The multiplicative inverse of A is dash. It is a multiple choice question, so we can apply the shortcut method. If capital A is a square matrix of order 2, then A inverse is equal to dA. That means place interchange of the diagonal elements. Place interchange of diagonal elements, and the sign change of the non-diagonal elements. Sign change of the non-diagonal elements. Whole divided by AD minus BC, which is same as determinant of A It will be discussed in determinant chapter. If A is a square matrix of order 2 for matrix of order 2. Inverse for square matrix of order 2. It is a square matrix of order 2. So we can apply the shortcut method. First, place interchange of diagonal elements. Diagonal elements means left top to right bottom. It is the diagonal element and it is the non-diagonal element. Sign change of the non-diagonal elements. B will be minus B, C will be minus C. Place interchange of diagonal elements. A will be D and D will be A. Whole divided by A determinant, that means AD minus of BC. So, A is the given matrix having elements cos of theta, minus of sin theta, sin theta and cos of theta. Implies this A inverse. First, place change of the diagonal elements. Place change, interchange. Place in the cos theta same. So it is cos theta, no change of the diagonal elements since both are same. Sign change of the non-diagonal elements. Minus sin theta will be sin theta. Sin theta will be minus sin theta. Whole divided by AD. A is cos theta, D is cos theta, cos square theta, minus 1 plus sin square theta, which is same as cos theta, sin theta, minus sin theta and cos theta. Cos square theta plus sin square theta is equal to 1. So the correct option is C. Place change, sign change divided by 1. So the correct option is C. Answer. The inverse of A, if A is equal to this, we can apply the shortcut method. Since it is a multiple choice question, we can apply the shortcut method to find the answer. So the correct option is C. Is the matrix having elements cos theta, sin theta, minus sin theta, cos theta. Clear? Okay. Note down.